Okay, good afternoon, everybody. Let's get going. Right, so let me go over a quick recap of what we did last time. So last time we talked about the investigation of normal minima, right? We have a surface or we have a function and we would like to find the points of minima. And by points of minimum, we mean a minimum point or a maximum point, whether local or global. And just to make the story short, in the scalar case, when the dimension is 1, the necessary and sufficient conditions are the derivative at the point of the function is 0, and the second derivative, if it's positive, then we have a minimum, and if it's negative, then we have a maximum. That discussion extends to the vector case. So in the vector case, instead of the derivative, we talk about the gradient and the Hessian. Okay, so this is the only difference. And to investigate the point for the gradient for the vector case, we need to study positive definiteness of the function that defines the Hessian. Okay, so we need to be able to know how to determine whether a matrix is positive definite or a negative definite. So this is the only thing that is different than the scalar case. But this is just the basic that we need to know. All of us, we need to be familiar with these notions, because after all, optimal control is nothing but optimizing a function, right? So we want to find these minimum points, right? And but in different, maybe complex ways. But this is the basic that we are going to build on. Okay, and this last example. The Hessian is neither positive nor negative. And that means that the point can be either minimum or maximum. And we call that point a saddle point. There's a name for that point. We call it a saddle point. So it's like a saddle, right? It's not a point. It's not like a point, but rather it's like a saddle. So it's a surface. If you look at the book by Athens and Falb, you'll see a picture. I believe it's figure 5.5, where you can see like a picture of a saddle point. Okay, it's beyond this course to go deep into these mathematical concepts, but we just want to know the basics, and we want to build on those basics. Okay. Any question about this stuff? Yes, go ahead.
Yeah. Since we proved that it's not a definite positive.
Yes.
So this is not enough for us to say there is no minimum in this.
Yes. Yes, exactly. And in fact, it's indefinite. So this is not a positive definite, nor a negative definite matrix. This is why I'm saying it's not minimum and it's not a maximum point. It's just a saddle point. And this is an example to show you that a point can be both not minimum and not maximum at the same time, even though it satisfies these necessary condition in this case. Yeah. Any question? Other question? All right. So now let me move to lecture 3. So I'm building my way up a little bit. Okay, I'm going from the basics first, right? The first lecture is about an overview of optimal control and you know, the differences in optimal control and optimization and data-driven optimization, right? Second lecture is a basic lecture about minima or minimal points, minimum and maximum points. Third lecture today, I'm going to talk about minimization under equality constraints. So before lecture 2, there was no constraints. We have a function, we want to minimize it and find the minimum points, right? In this today, in today's talk, we'll address this point here, which is, and to make the presentation tractable and not confuse you guys with notations, I'm going to focus on the two-dimensional case. But whatever we're going to talk about is going to be extendable to any dimension, any dimension, okay? But let's now focus on two-dimensional case. Okay, so x is a vector, x1 and x2. We have functions of these vectors, so a function of x and another function, g of x. And now I need you to pay attention here. So, and I need you to read the book, right? So this is an attempt to simplify. In the book, in my opinion, it's a little bit more complex than what I'm doing here. But these slides should convey the message of the book, okay? Athens and Fall, right? Chapter 5. All right, so we have two functions, f and g of x, where we assume that both are continuously differentiable in a domain D in R2, okay? Here's the problem. The problem is minimize the function f subject to x being belonging to this specific domain, and we want also to satisfy this constraint. G of x is equal to 0. Right? I'll give you an example later on, but we can come up with other examples later on in the course, right? But the concept of constraint we find it in our lives, right? We want to minimize for example, a fuel consumption, while at the same time we don't want to we want to go at a speed, constant speed. So we have to go at a constant speed but minimize. Sometimes these constraints even they seem contradictory, okay? But my point here is that constraints are natural definitions of problems that we face in our lives, okay? This is the mathematical representation of that. And of course, as you can see here, there is also something special to this problem, and that is the equality constraint. So it's not larger than or equal to 0 or something, right? It's just g of x, a function of x, right, is equal to 0. Admittedly, you know, this is the simplest version of constraints. The inequality constraints are a little bit harder to deal with, and I'll talk about that later in the course. But now, this is a problem of equality constraints, okay? We have an equal sign here. So in lecture 2, we dealt with the first part of the problem. Minimize f of x subject to x belongs to D, okay? Now we are adding this constraint. So we want to satisfy this constraint at the same time, right? So how can we do that? So there are different ways to do this. I'm going to take the approach of perturbation. I did that in the previous lecture. I'm going to do that also in today's lecture, okay? So this is one way to derive necessary and sufficient conditions for optimality, okay? Through what we call perturbation. So basically, what we do is we go to the minimal point and we perturb by small variation, okay? And see what happens, okay? That's the idea here. So let x equal to, so here I'm going to perturb the minimal point. So I'm going to assume that there is a minimal point. I'm going to perturb it. In this case, the point is a vector, is x1 and x2. right? So I'm going to perturb it by epsilon. Epsilon is a parameter, a small parameter, okay, times c. C is an arbitrary vector, right? So you cannot add a variable to a vector. You have to add a vector to vector, okay? So I'm adding an arbitrary small perturbation vector, to x star, okay? All right, so now we want to investigate the perturbation of this minimum point. One more thing I'm going to use here, which is Taylor series expansion. Taylor series expansion is an expression of any nonlinear function, okay? As long as it's continuously differentiable, okay? And so this is a one form of Taylor series expansion when around this point here, around this point. So f of x can be expressed as f of x star plus epsilon, right? Here, this is the gradient, okay? Remember, x is a vector, right? So this is the gradient, df with respect to dx1, right? X star, xc1 plus, and remember, xc here is also a vector, okay? So this is a vector, this is the gradient, okay? And epsilon is just a parameter, plus order of epsilon. So plus other terms, other higher order terms of all of them multiplied by epsilon, okay? All the order terms multiplied by epsilon, and yeah, so this is what we have. We can do the same for g, right? Both of them are nonlinear functions. Both of them are continuously differentiable, okay? So we express g of x as a Taylor series expansion as well, okay? Now, it is given that g of x is equal to 0. That's the constraint. So we need to respect that all the time, okay? So g of x is equal to 0. X can be anything, right? So when you are given g of x is equal to 0, x is anything. So we can, which means that g of x star is also equal to 0. Okay, so gx of star is equal to 0. Okay, so what that means is this will go away and this term will go away. Okay, and spell this out. So this is like dg over dx1 of evaluated at x star c1 plus dg over dx2 evaluated at x2 evaluated at x star c2, or both of them multiplied by epsilon. Take epsilon as a common vector, common factor from both, right? Plus order of epsilon. So we have this one. Okay. You'll see where I'm going with this one. All right. So divide both. Take C2 to the other side. Take this term to the other side, multiplied by epsilon to the other side, and divide everything by epsilon. Okay, you'll end up with this. You'll end up with this expression. Okay, and also divide by dg over dx2, or partial g by partial x2. You will get this expression. Okay, so you have that expression, right? We are going to assume that the partial derivative of g with respect to x2 evaluated x star is not equal to 0. So that's an assumption that we have to make. Yeah, so for the mathematics to be tractable, okay? Because we cannot divide by 0 here. Okay, so now we have that. Take C2, right? Substitute into the expression of f, or the Taylor expansion of f, right? So take that, substitute it back in the expansion of f, and take f of x star to the other side. So you have f of x minus f of x star is equal to epsilon. Take it outside as a common factor. df over dx1, x star, c1, plus df over x2, x star, and instead of x2, right, substitute by this one here. you get that. You get this expression here, right? So you can easily verify this line here. Okay, so we have that, and then take xc1 as a common factor from this term and the other term. Okay, so take it as a common factor there. Okay. Okay, so now we have that. Here's the point. The point is, we are assuming that x star is local minimum. Okay, so this is also the assumption here, because this is a minimization. Okay, so x star here is a local minimum. So since x star is a local minimum, fx minus fx star is larger than or equal to 0. Fx minus fx star, right, is larger than or equal to 0. Because of that, the right-hand side must be larger than or equal to 0. And for that to happen, and we'll not have any conflict, right, this coefficient must be equal to 0. It must be equal to 0, right? Because this is larger than or equal to 0. If this is negative, then we are screwed. Then there will be a contradiction, right? For this to be a local minimum, this coefficient must be equal to 0. All right, so take that. So this is the condition now that we are going to work with, okay? Remember, why are we doing this? Why are we going through this path here? Let's go back to the problem here, right? This is the problem, right? We want to minimize f. We know how to minimize any function. Take the derivative and take the second derivative just to see which minimum that is, right? And take the derivative, equate it to 0, get the point. That point is a minima, and then see whether it's minimum or max, right? That's how we do it. But the problem is in the constraint. How are we going to deal with this constraint? How are we going to satisfy this constraint? Right? That's the problem. And this is why we're doing this. We want to find a practical condition to deal with for optimization, right? This is why I'm doing this, okay? Otherwise, how can you solve this problem? Okay? So we are here now. We are here, okay? We have achieved, so what we did is, okay, perturb the minima or the local minimum, right? Express the functions in Taylor series expansion, do some massaging and manipulation, and because x star is a local minimum, right, then we end up with this condition here. Now look at this condition here, okay? So this is the condition, right? This condition is nice because it takes into account f and g at the same time, right? And all of these terms are evaluated as x star, at x star. So this is a promising condition to work with, okay? Because x star is known. And one more thing that is also promising about this condition, and that is these terms are all scalars, right? This is a scalar, this is a scalar, this is a scalar, this is a scalar. It's always nice to work with the scalars than vectors, obviously, right? So that's nice, and this is promising. Now, just to take it to the next level, right, comes Lagrange. Lagrange is I believe it's this technique that I'm going to describe in a minute is named after the scientist Lagrange, a French scientist, but I'm not sure 100%. Okay, but anyway, let's assume that Lagrange came and say, okay, I'm going to define now this term, the minus the partials with respect to g of g with respect to x, right, as rho star. We call that Lagrange multiplier. Okay, and see how that is going to help us solve the problem, right? So this is what's known as Lagrange multiplier. It's a well-known technique in optimization. Okay, and this is the story behind it. Okay, or this is a motivation behind it. The motivation is to solve the equality constraint problem. Okay. So define the minus and this term as rho star. Then this condition can be written here like this, right? Partial f with respect to x1 evaluated at x star. Remember, evaluated at x star. So this is not an unknown. This is like a definite term. We know what its value is. It's not in terms of x, where x can be anything. No, it's at x star, right? Then rho star dg over, or partial g over partial x1, x star is equal to 0. Okay, I just took this definition, put it here, right? And no, I think in the way I explained it, I think I did the wrong thing. Actually, the Lagrange multiplier, it's not this one. It's this one, df over dx2 over dg over dx2. So it's this one. I can use my notes. Actually, this is what I'm doing. I circle it using a red line. So this is the rho star. This is the rho star. Okay, this is the Lagrange multiplier. Okay, partial f with respect to x2 over partial g with respect to x2. Okay. Now these two equations will show you why this definition makes sense. Because look at once you do that, right? So then you have the partial f with respect to x1, right? Rho star partial g with respect to x1, right? And you could do the same for partial f with respect to x2 plus rho star partial g with respect to x2. Okay. Rho star is just a scalar, okay? And then we have g of x, and this is the third condition. We have g of x star is equal to 0. Now, if you look at these equations, right? These equations are now two linear equations in two unknowns, right? And you'll see in examples how we're going to solve that. Okay. So alternatively, define now capital G. Yes, go ahead.
I'm still kind of confused on how we determined our Lagrange multiplier.
It's just a definition.
So it's always going to be that.
Yeah, it's always going to be that, and there is a reason why it's defined that way. I'm saying the reason is it's going to give us necessary and sufficient conditions for optimality. Just bear with me until I finish the next couple of slides, and then we'll revisit that. Okay? Yeah. Okay. So, but take it from me. This choice is strategic, and it's going to help us solve the problem. Okay? So define now capital G as a function of x and rho, right? Which is going to be equal to f plus rho g, right? And g of x is equal to 0. Okay? So now here is the stationarity, what we call stationarity conditions, right? Now we are going to reframe the problem, the optimization problem of f satisfying the constraint into this problem. Now look at this problem here. Minimize g, which is a function of x and rho, subject to x belonging to the domain, and rho is a scalar. So if x star and rho star is a local minimum, right? Then according to up to this point, right? and because X star is a minimum, then X star is a minimum, then rho star is also minimum. So keep in mind that we have rho and then we have rho star. Rho star is the Lagrange multiplier. It's the optimal scalar value that solves the problem, right? So if X star and rho star is a local minimum, then the partial derivative of g with respect to x1, which is we are going to differentiate this with respect to x1, right? Is equal to partial derivative of x with respect to x1 plus rho partial g with respect to partial x1. Similarly, when I differentiate g with respect to x2, I get partial f with respect to x2 plus rho partial g with respect to x2. And then when I differentiate g with respect to rho, obviously I'll end up with only g of x here. Now the question to you guys here, right, is when so this is my definition. So this is the definition of g, right? So so I'm going to minimize, because X star and rho star are local minimum, right? Then, I minimize G with respect to X1, X2, and rho. My question to you now, when I minimize G with respect to X1 and X2, why don't we also differentiate rho with respect to X1 and X2? Why rho is just here treated as if it's constant?
Because it's a scalar, if you differentiate it, it would be zero anyway.
Well, no. Yeah, it's scalar, yes, but it's not because of that. It's okay. It's a scalar. It's a scalar constant. This is the keyword. It doesn't depend on x. So here, rho star depends on. So remember, this is taking the derivative of f with respect to x2 evaluated at x star. So it's a number. And this is a number. So it's a number divided by number is a number. So this is rho star. So rho in general is just it's a scalar number. It's not a scalar x. It's not x1 or x2. You know what I mean? It's not a scalar variable. It's a scalar constant, right? Because it's independent of x, right? Then it appears as if it's a constant here. This is the reason here. Whereas obviously f depends on x and g depends on x. So when we differentiate capital G, right, we differentiate f with respect to x1, right? We treat rho as a constant, and then we differentiate g with respect to x1. That's the reason, okay? Okay. This is the main slide. Okay, this is the main slide here, okay? And I want to take a minute to observe this slide, okay? This slide is the result of what we've done here, okay, in the previous two slides. So where we are here, we started from a constrained problem, which we don't know how to solve, right? Now, that problem is now cast as optimization problems. Remember, optimization means like derivative is equal to 0, or derivative is, or second derivative is negative or something, right? So we deal with optimization by differentiation. So now we converted the constraint problem into these three conditions. All of them are based on differentiation. You will see later on how we are going to use that to solve a problem, to solve examples. But this is a reformulation of the problem. This is my main point here, right? We reformulated the problem so that we have these three conditions. Okay? So then these are very important remarks. The first remark is that the Lagrange multiplier, right? It's strategic because it converts a constrained problem to an unconstrained problem, right? In all these three conditions here, There is no constraint. There is no, and by constraint meaning, a static function is equal to 0 or less than 0, right? There is no constraint here, right? All these need to be minimized. All these three conditions need to be satisfied and minimized. Okay, so this is the key, right? The Lagrange multiplier converts a constrained problem to an unconstrained problem. And the second one is just technical, meaning that one, either the partial of f with respect to x1 or partial of f with respect to x2 must be non-zero, otherwise the problem cannot be minimized. This is a technical problem. For the problem to make sense mathematically, okay? Any question up to this point? Yes.
What about the second derivative?
What's that?
What about the second derivative?
Of G?
Either f or g.
We are dealing with a local minimum, so we are assuming that we are dealing with a local minimum. So we don't need. You can do the second derivative just to confirm that the solution to this problem is indeed a minimum solution, by taking the Hessian and making sure that Q is positive definite,
Should we do it or?
No, you don't. You can do it as a sanity check, as a check. But yeah.
Because in the lecture 2 that we have like the
Yeah, lecture 2, we don't know the point, whether it's minimum or maximum. Then you do that. But you do the second condition only if you want to double check that the solution that you have is indeed minimum or a maximum. Yeah. But remember, in these problems, we want to find the minimal solution. That's it. That's all what we want, right? So we want to minimize and find the minimal solution. Okay, so this is, remember, this is for dimension 2. So this is a special case, dimension 2. Let's now generalize this to x belonging to Rn, right? So n-dimensional system or function. We call this the general Lagrange multiplier form, right? General Lagrange multiplier form, right? Minimize, this is the problem, minimize f of x subject to g of x is equal to 0 and x belonging to a domain, okay? All right. As I said, x and g, x here is a vector of dimension n. Okay. So I'm going to add another condition here, which is the gradient of G has a full rank. The gradient of G, you will see, and the reason for that is it guarantees the solution exists. It guarantees that the solution exists, okay? So meaning if you stack the gradient of, so remember this, I'll give you an example later on, but basically assume that the gradient G1 of x up to, if you stack them in like vector 1, vector 2, in a matrix, right? And that matrix has m columns, then that matrix will have rank m, full rank, right? And this em are in general less than or equal to n, okay? So this is like the number of constraints, right? So m here, small m, is the number of constraints, okay? So remember, g, function g is the constraint. So and this is why this is a general, this slide is a generalization, right? Remember, in this case, here we are assuming that only one constraint, G, right? But here I'm assuming M, small m, number of constraints. And the condition on these constraints is that if you stack them in a matrix, column by column, then the rank of that matrix has to be equal to m, the number of constraints, for the problem to be solved, okay? Keep that in mind. Right? So this assumption guarantees that at each point in the domain, we can solve the equations g1 of x is equal to 0, g2 of x is equal to 0, right? In the neighborhood of that point, to express the n minus m components of x in terms of the remaining m components. Yeah, I know, this is just jargon for me saying we need these constraints to be solved, right? For them to be solved, if you stack them in a matrix, they have to have full rank. That's the point here. All right. Okay, so now define an n minus m dimensional manifold, right? Hyperspace in Rn. Okay, and so let capital G, right? This is now we are. This is the genius of Lagrange multiplier, right? It combines the constraint in addition to the function we want to minimize in one equation. Okay, and then we are going to deal with this equation. We are going to minimize this equation as if it's unconstrained, as if there is no constraint, right? And how are we going to do that? This is the link by the Lagrange multiplier, rho transpose. Okay. In this case, in this general case, the Lagrange multiplier will be multipliers. We'll have m number of multipliers, one for each constraint. Okay? So we have m number of constraints and m number of multipliers. Okay? Okay, so then we'll end up with not two, but there will be n plus 1 equations, but basically in general two conditions, right? This condition, you differentiate this with respect to x, right? X being a vector, so you do it for each xi. And in addition, you extend this one, you differentiate g with respect to the Lagrange multiplier, which is going to be equal to the constraints, right? Because, you know, if you look here, right, if you differentiate this with respect to Lagrange multiplier rho, you have dg over d rho is equal to just gx. This is equal to 0 because it doesn't depend on the Lagrange multiplier. Okay? So this is why we have that, and this is why we have that here. Okay? So these two right, are what we call the necessary conditions to solve the minimization problem for the constrained problem. Okay? Okay, so now let's write it in a matrix form. So necessary conditions, if x star belongs to a domain, is a local minimum, okay, subject to constraints. Then there exists a rho star. In this case, rho star is a vector, right, of dimension m, which is the number of constraints, right? So it's a vector of scalars, such that, right, this equation is this equation written in a matrix form, right? The gradient of f, right, plus the gradient of g rho star must be equal to 0, right? I mean, that's, if we want to minimize, that's what we want to do. We want to equate this equal to 0, and we want to equate this equal to 0, right? And see the second, and this is also one of the nice things about this approach, is that it comes in full circle because we want to minimize these two, right? Sorry, we want to minimize this one. We take the derivative and then we equate it to 0. With the derivative with respect to the variables, and then we equate it to 0. So you take that, you equate it to 0, that will give you that. And then when you equate this when you take the derivative of that equation with respect to O, right, and then equate this to 0, you will end up with the equation of constraints to begin with. Okay, but The constraints at X star. This is like not constraint in general, constraint at X star. Okay, I'll give you an example and then you'll see how we're going to do this. Okay. Okay, here's the example. Yeah, but before I go to the example, is there any question? Okay, let's move to the example. So here's the example. Minimize this function subject to this constraint. Okay? So this is a function, a nonlinear function. The function is a function of a vector of 3 elements, x1, x2, x3, subject to a constraint. I have only one constraint here in this case, which is this one. All right, this constraint is not in the form that I gave you. In the form I gave you, g of x is equal to 0, right? This is something is equal to 3, so we need to do something about that, okay? So before we do something about that, what is this problem? If you look at this problem is nothing but a minimization of distance squared from a point on a surface, 3D surface, 3-dimensional surface. So we have a 3-dimensional surface, okay? And 3-dimensional surface, okay? We have a point on that surface. We want to know the minimum distance between that point and the origin, which is 0 and 0 inside the surface, right? So think of sphere. Sphere is the ideal case. Sphere is a point on the sphere is going to be the same on every all the sphere, right? So sphere is an example, but then it will not be the point, it will be the whole surface of the sphere, right? But think of a 3-dimensional case where it's not a sphere, right? So where is the minimum point between a point on the surface of that subject or that object to the origin, 0, 0, and 0, okay? That is that problem. How can we find that minimum point, right? We can write it as, right, this is the equation that describes this surface. It's a linear equation, so it's a surface equation, right? So this is the equation that determines the surface, and this is the equation that determines the point, because the point, what is the point? The point is the square root, right? Pythagorean theorem, you have the square root of x1 squared plus x2 squared plus x3 squared, right? If you take the square root of that, I mean, it doesn't matter if you take the square root of not, but it's easier to square it, okay? Working with the square root is not good, especially for differentiation. My point here is that if you minimize the distance squared is the same as minimizing the distance, right? That's the point. So this is why we work with minimizing distance squared easier, because we avoid differentiating the square root. Not good, okay? It's complex. Okay, so this is the point. It's a very interesting practical problem, okay? In this problem, the distance is the function that we want to minimize, and the surface of the object is the constraint, okay? So what we did, how we deal with the constraint, we take the 3 to the other side. So then the constraint g of x is x1 plus x2 plus x3 minus 3 is equal to 0. So in that case, now we put it in the form that we know, the formal form, okay? So it's that, g of x is that, and f of x is that, okay? We go back to the general case here, right? In the general case, this is going, this condition is not going to be needed in this case because I only have one constraint. So in the one constraint, this is redundant. But anyway, I'm going to show it to you just so you know, all right? So if you take the gradient of g with respect to x, you end up with, well, x1, 1, 1, 1, nothing there, okay? So it's 1, 1, 1. Okay, and because I have only one constraint, it's just one vector. And obviously one vector has one rank 1, okay? I guess unless it's all zeros, in that case it's, which is, all zeros, that means we don't have a constraint to begin with, okay? So the rank is 1, right, which is equal to the number of constraints, so we are good, okay? Which means, okay, so this is just yeah, extra point here. Okay, now we go to these two conditions. These two conditions to solve the minimization problem, these two conditions. Okay, so the first condition is, so this is like in terms of, these two equations are the same. This is in the matrix form, this is like in a component by component form, okay? So take that one, right? We call these stationarity conditions. So partial f with respect to x1 plus rho partial g with respect to x1 must be equal to 0, right? So let's do that. Partial f with respect to x1, that would be 2x1 plus rho partial g with respect to x1, oops, where did I go? Which is equal to 1. So you end up with 2x1 plus 1 times rho. That's rho. Because of the similarity of the equations, you can see that that's the same for x2, that's the same for x3. So I wrote them all in one equation in terms of xi. Okay? So you end up with 2xi plus rho is equal to 0. It's one equation with two unknowns. I need another equation to solve. Okay? Guess where the other equation comes from? Well, the other equation comes from this one here, right? So take the constraint. So from here, just to take rho to the other side, right? And so you have x1 is equal to x2 equal to x3 is equal to minus rho over 2, right? From this equation here, okay? All right, now substitute into the constraint. So when you substitute into the constraint, right? So you have x1 is equal to x2 is equal to x3. So you have 3 times minus rho over 2, right, is equal to 3 from the constraint. Okay? From there, you find rho. Rho is equal to minus 2 from the constraint. Take rho, minus 2, put it here, you'll end up with 1. And that is the minimum point. Right? And if you plug it in here, the minimum distance is going to be equal to 3. 1 squared plus 2 squared plus 3 squared. So the minimum distance is going to be equal to 3. Okay? And yeah, so that's the solution to the problem. Okay, so let's go back and appreciate the solution, right? Had I told you, minimize this equation, right? Then you would differentiate with respect to x. You find the gradient equated to 0, find x, we're done. Okay, but the problem here is, I mean, I shouldn't have said, okay, you could do that, right? But also you could minimize this one here, right? Minimize this function, take the gradient, equate it to 0, find x and find it. But now to minimize something and make sure that the solution also satisfies another constraint, that is a harder problem. And this is how we solve it using the Lagrange multiplier. Okay, that is the, and just as a sanity, as a check, you can do, as Anna said, do the second order condition, right, to check, right? So you can do the Hessian. You can do the Hessian, and also you can do this. You can take the gradient of the constraint, transpose times y is equal to 0. We call this the, there is a name, the perpendicular, I think. There's another one. Anyway, this is the well-known fact about tangent space. Just as a check, and you'll see that this will also checks. This will give you 0. For more on this problem, you can consult this book, Linear and Nonlinear Programming, by Leonberger, page 226. Okay, this is where I got where we got this example from. Okay. All right, any question? All right, so today I'm going I'm just going to introduce next lecture now, okay? I'm not going to, so next lecture is a little bit involved, so I'm not going to go deep into it. I'm just going to just introduce it, and I would like you guys to read sections 5.7, 5.8 in preparation for next lecture, okay? Now we are going to go another level, which is dynamic systems. Lecture 2, lecture 3, we've been dealing with static functions. Static functions. F of x is equal to something. We call that static function, okay? Once we consider x dot is equal to f of x, now we are dealing with dynamic systems. Now we are dealing with cars, with rockets, with motors, with things that are dynamic, okay? Okay, so but lecture 2, lecture 3 is just static optimization, okay? You have a function, we want to minimize it, right? Either unconstrained or constrained. Now we're dealing with dynamic systems. Okay, the first one we are going to deal with is what's known as fixed time free endpoint problem. And the approach that we're going to follow is known as variational approach, which is the main approach that is that defines optimal control. Okay, so what is this problem? Consider a system, x dot is equal to f of x, u, and t. So it's a nonlinear system. It could be time varying, right? And it has a u, has an input, okay? Initial conditions are known. So the initial conditions of the system are given and known, right? We want to minimize this cost function. J, function of essentially u, but also it's a function of other things, right? It's a function of x, obviously, and t, right? But our interest in u, okay? So j of u is equal to a function of x at t1. So this problem is defined over a horizon. The horizon is from t naught to t1. T naught is the initial time, t1 is the final time, okay? So you have a function of x at t1 at the final time, plus the integral from t naught to t1, another function of x, u, and t with respect to time. K and L, we define them. We, the users, define them. Okay, they will be given to us, or we define them according to the application at hand. Okay. As I said, the initial condition is known, so T naught is known, and x at T naught is known. Also, we are going to assume that the final time is going to be given to us, right? So T1 is going to be given, okay? Hence, it's fixed time. So we are going to consider an optimization problem in a fixed time. You have 1 hour, right? I want you to optimize or minimize this cost function. I don't care about the final state, right? The fuel in the tank, I don't care. Whether it's 0 or full tank at the end of the experiment, we don't care. As long as we minimize this cost function, okay? This is why it's called free endpoint, because we don't care about the final state, right? And fixed time because T1 is fixed. So it's fixed time, free endpoint problem. Okay, we'll consider later on different variations of this problem. We are going to consider also what happens when we want to minimize time. Actually, we do care about time. We want to optimize this cost function in the minimum time possible, right? But in this case, we don't. The time is fixed. Okay, so we will not focus on minimizing time or optimizing time, but rather we want to find u, right, that minimizes this cost function. F, L, and K are obviously as the typical assumption we make throughout this course. All the nonlinear functions are assumed to be sufficiently smooth. By sufficiently smooth, meaning continuously differentiable. So we can continuously differentiate them, and every time we differentiate them, the result will be continuous, right? So this is another way. You can see it also in papers, right? Instead of continuously differentiable, you can also see sufficiently smooth. Okay? U is unconstrained. So in this problem here, there is no condition on U, right? U can be anything, right? As long as it's a piecewise continuous function, right? So piecewise continuous function, meaning the finite number of jumps, okay? So the problem is find U to minimize J. That is a problem, and we are going to solve this problem next lecture, okay? Any question?
If there's no G of X,
What's that?
there's no G of X.
No constraint. No constraints. Yeah, it's yeah, it's there is no constraints. So, yeah, so this one, of course, doesn't answer your question. U is unconstrained, but also there's no constraint on X. Yeah.
I was just curious, like an example, like a real world example.
Yeah, I'm gonna give you an example next week, but let me think about. So, for example, a typical example of this is when we want to minimize X. All the focus on X during the experiment. So what is X? X could be the height, could be the speed of the car, could be the position of the mass. You know what I mean? So, these states. Depending on the application. So we want to minimize the state of the system during a fixed time of the experiment. We don't care about U, right? You could be anything, and but the only thing that is given to us, and which makes this a little bit interesting, this problem, is that T1 is, we don't have up to infinity to do it. We only have it in fixed time, which means that T1 being 30 minutes will end up with U. T1 being 30 hours, maybe we'll end up with different, you know what I mean? Different. So the controller is going to depend on the T1, all right? So yeah, so that's the idea here. Okay. All right, thank you very much. I'm going to upload homework 1 soon, hopefully before next lecture, okay? Homework is going to cover the concepts that we covered last week and this week. All right, thank you guys, and see you next lecture.